So let me start this situation here. That is the binomial-beta case. So let's do an example. So we want to see if a coin is fair or biased. So we times say and heads 52 times. So we say that H0 is that is fair. Well, let's say let's first write the situation. So let's say X is the number of heads in 100 tosses. So X will be binomial 100 and theta. This theta in fact is the T. Okay. Now we say that let's say H0 is that theta is less than or equal to 1/2, and H1 is theta is bigger than 1/2. So, and each one happens, each has probability 1/2, which means P of H0 is P of H1 is 1/2. Right, so this is, and I need, this is in fact theta. It should be the random variable, so, and I make this assumption this theta itself has beta distribution, and I chose what did I choose? I chose beta. I can't remember what I chose here. Beta 3. The beta distribution, beta is alpha beta. These are the two parameters for beta distribution, and beta distribution has is between 0 and 1, so it has support. Its support is 0, 1, which means that it looks like this. So let me. So this is the premise. Now let me erase this. Beta distribution is in fact an amazing choice when it comes to probabilities, because this is probability, and the reason is that it is a number between 0 and 1. This is where is that? What is 1? Yeah, so let's just. So beta distribution, this beta 3 looks like this. 0, 1, it's something, well, I have a graph of that. So it's like, and this is 0.5 and 1. So f beta PDF of beta 33. Okay, so I chose this for theta, in fact. And since it's between 0 and 1, it makes sense because theta is takes the values between 0 and 1. And that's probability. So it is a number between 0 and 1. So let me continue with what. So it's cold. Okay, so well, let's see what happens to. So the prior is theta, which was beta 33. Okay, so let's see what we have here. So we need that f of x theta. Then if I divide f x theta by f xx, which was the marginal distribution, I would get. So if I divide it by this, which I also denoted this by hx, then that is theta given x. That's the posterior, right? Well, what is this thing? So let me write it down. So the top, in fact, is f of x given theta times pi theta. Okay, divided by this. So I need this times this, divided by this. What I will do is this. I can find this, it's okay, although it's not that hard to find it, but one thing we can do, and we usually do, is we write it down and just forget about the constants. And just look at the structure of the end result, and we just say, okay, this looks like, say, beta distribution, therefore the constant also follows. So we don't have to find those constants. In fact, this is like a constant. This is like a constant, and there are some constants involved here. So let me write it down and then I'll tell you what I mean by this. So, first of all, let me write down pi theta. Pi theta is the PDF of this beta 33. So pi theta is a PDF of this, and that is gamma 3 plus 3 over gamma 3 times theta to the power 3 minus 1 minus theta to the power again 3 minus 1. Okay, so that is pi theta is some constant. This is gamma 6, gamma 3, gamma 3. The important thing is this. So this is the constant. This is what I see a constant. Okay. So I need I have 52 in 100. So let's erase this and f of x given theta times pi. Theta is, that one is 100 x, say, times theta to power x, 1 minus theta, 100 minus x. But that was, in fact, x was 21, right? So let me write this thing here. So times gamma 6 over gamma 3 squared, and theta squared, 1 minus theta squared. Okay, so now that x here, we observe 52. So observe x is 52. So observe x 52, that's the small x, so f of x theta pi, theta in fact is 152, and theta to power 52, 1 minus theta to power 48, right? Okay, so and that is times gamma 6, gamma 3 squared, theta squared, 1 minus theta squared. Okay, so this will be some constant that is 152 times this constant. This is also like 5 factorial over 2 factorial squared. I don't care what that is because that's just a constant. Then theta to power 54 and 1 minus theta to power 50. Okay, so let me see. Well, I guess I had what? Something is. Yeah, that's correct. So that is correct. So that is. So let me erase this thing and the posterior will be xc theta given x is 52 is this thing let's call this some constant k, well, no, not k, because I would use k for spontaneous. So let's just write c, c1, 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 theta 54, 1 minus theta 50, divided by this. And this is also a constant, c2. So that's a constant, c2. So what I see here, if I just ignore the constants, this, the PDF, which is this thing, is, this means it's proportional to this, theta to the power 54, 1 minus theta to the power 50. So I'm just ignoring the constants. But that is what? That is, on the other side, this has to be, it looks like what? It looks like a PDF, part of the PDF of a beta distribution. What beta distribution? So this is alpha minus 1, and this is beta minus 1. So this should be beta with alpha equals 55 and beta 51. So without even looking at the constants, I don't care what the constants are, I can find this, that's okay, but in the end, in fact, I have given it like that in the notes. If you look at the notes, you will see that eventually we will get this. So I have the posterior distribution. So what I will do is in fact this. So I have to find these two probabilities. So I have to find these two probabilities, T of H0, given that x was 52, and this is based on what? This is based on this distribution for theta. So this is in fact P of theta, this is big theta less than or equal to 1/2, given that x is 52, which means given this, right? So let me so that is in fact from 0 to 1/2. That was c of theta, given x is 52, d theta. So what was that? That is in fact a beta distribution. Remember, that was PDF of beta distribution, so that is integral 0, 1/2. I had it, so that was gamma, what was that, 55, 51, what was that? I can't remember, 55, 51. I think it was 55, 51. So that will be 55 plus 51, gamma 55, gamma 51, theta to power 54, 1 minus theta to power 50, d theta. Okay. So that is in fact and I calculated this and I found 0.6517. So it's almost a 0.6517. So you see, I used the posterior distribution to calculate the probability of H0 happening given data. So that's H0 happening given data. H0 is a statement on data, and I use the posterior distribution for data to find this probability, and in fact I found this because of this, with this assumption. So in fact this is part of the calculation. So anyway, that is for this one, and then the other one will be P of H1 given X is 52 is in fact the complement of this, that is P of X bigger than 1/2 given X is 52. So that's the complement of this, that's 1 minus 0.6517, that is 3482. 3482. So if I divide them to find the if I divide them, I will get that K is in fact P of H0 given X is 52, and P of H1 given X is 52. And dividing them will give me something that I found 1.80, which is quite good. K is about 2, which supports 80. Okay, so we state that there is enough evidence to accept 80 or support 80. So that evidence that is 52 out of 100 is a good indication that theta in fact is less than or equal to 1/2. Now you might say, why did we do this less than or equal to 1/2? If I say x equals, theta equals 1/2, you see the distribution that I found is beta distribution. That is a continuous distribution, saying that theta equals 1/2. That will give me 0. Remember, for continuous distributions, statements like that, probability of x equals something is basically 0. It has to be like an interval to make sense. And that makes sense when we have discrete distributions. So if you want to check something like that, in fact, I have given you problems like that, or solved some problems when you assume that it is equal to something. But if you are using this distribution as prior beta distribution with binomial, then the hypothesis should match what you are doing. So the hypothesis should be something like an inequality rather than equal to something. Okay, so let me erase this and write down the general form of this thing. So the binomial beta is this. Binomial beta, well, it doesn't have to be a coin, it can be like you play a game, for example. So the binomial beta is, in general, is this. X is binomial, and you do an experiment n times, and probability of success is unknown. So, but that's a number between 0 and 1, so that's the p. And we assume that theta is some beta distribution with alpha and beta as parameters. Okay, so xc of theta given x, so observation is this. observation observe x equals small x, right? It was like x equals 52 out of 100. So in our case, n was 100 and x was 52. So we observe this. So xd of theta given x, that small x, will be f of theta x theta pi theta divided by fxx, which I denoted this by hx. So this is constant, and there are some constants coming out of this. So let's write down the parts that have theta. So this one, remember, it has like nx. So this one has an nx times blah blah blah. But what is that blah blah blah? The blah blah, in fact, is theta to power x times 1 minus theta to power n minus x. This comes from the binomial. Then I multiply it by pi theta. Pi theta has, again, gamma alpha plus beta, blah blah blah. But it also has theta to power alpha minus 1, 1 minus theta to power beta minus 1. That's for this. And some constants. This is also a constant. So I don't care about the constants. So this looks like theta. I have alpha plus x minus 1, 1 minus theta, beta plus n minus x minus 1. Okay, so this is a part of beta, a beta distribution. So I can conclude that my posterior distribution is this. So posterior distribution, by looking at this, becomes posterior will be beta, and remember beta is this plus 1, so that's alpha plus x, and this one plus 1 is beta plus n minus x. So posterior has this distribution. And remember, the prior was what? The prior was beta, alpha, beta. So that is posterior if we have binomial as the distribution for the experiment. Okay, so that was this situation. There are other situations. Yesterday I discussed normal, when the distribution is normal and you take the theta, which in that situation was, that case was the mean, take that to be normal too. And you ended up with normal. That was amazing. So this one, binomial beta, and you see why this happens, because binomial has this in its structure, in the structure of PDF, and beta has something similar in the structure of its PDF. And these two, when you multiply, you will get something which is looks like beta again. So that is a story of binomial beta distribution. Okay, so let me stop recording this thing.